Section 1.3 is algebraic expressions. I can evaluate algebraic expressions, and I can simplify algebraic expressions. Big ideas here. Some mathematical phrases and real-world quantities can be represented using algebraic expressions. Variables can represent quantities in real-world situations and in patterns. And the properties that apply to real numbers also apply to variables that represent them. In example 1, we're modeling with algebraic expressions and writing an algebraic expression for the word phrase. 7 is a key number, so I'm going to circle it along with a number t. Fewer than is math action words. So we got to figure out what fewer means. It's minus, fewer means minus, subtraction. And this than is important because it tells us that we're comparing. So it tells us that we started off with some number t, and now we have 7 less than that. 7 fewer than a number t means we started with t, and then we subtracted 7. Now feel free to pause here and give this a try if you'd like. 2 times the sum of a and b. We have 2 times the sum of a and b. Times is a math action word, and sum is a math action word. So 2 times means multiplication. Sum means we're going to add, but it also tells us that we're multiplying that entire sum, the entire thing that was added together. So that has to go in parentheses because we need to have that sum before we can multiply. And according to PEMDAS, we'd have to multiply first. So we have to put it in parentheses so that a plus b comes before the multiplication. So 2 times the quantity, or the sum, a plus b. To model a situation with an algebraic expression, do the following. Identify the actions that suggest operations. Define one or more variables to represent the unknowns. Here it's important, guys, that we actually define those variables. Instead of just picking letters, we say what they mean, especially if you're just going to use x and y. If we're talking about cost and we use c, it's pretty straightforward, but we also want it to be something that we could look at and not know the situation and still figure out what it's talking about. So like W, for example, could be week, could be wages, could be weight. So a lot of different things there. So make sure that we define those because we want to be able to read this mathematical expression and know exactly what it's talking about without having read the situation. Represent the actions using the variables and the operations. So you start with $20 and save $6 each week. What algebraic expression models the total amount you save? Algebraic here tells us we're going to have variables, and we have unknowns here. So identify the actions that suggest operations. Save tells us we're going to add. It's going to increase. And each tells us that we're going to multiply. Okay, we got to come up with our variables. So we start with $20 and save $6 each week. We want to know how much total money you save. So the thing that's going to change here, guys, is the number of weeks. I'm going to use W for weeks. Okay. And now we can represent our actions. And it just wants an expression, so we don't have to have like equals the amount of money saved. So we start with $20. Start, I guess, could have been a math word too if you wanted. And we save, so we add $6 each, means we're going to multiply times week. 20 plus 6W. And that's going to tell us how much we have after W number of weeks. Feel free to pause here and give this a try. Let's say you had $150, but you're spending $2 each day. What algebraic expression models this situation? Okay. So again, pick out the things that indicate an operation. Spending tells us we're subtracting, and each tells us we're going to multiply. And we need to figure out what our variable is. Here, the amount of thing that's changing is how many days go by. So I'm going to use D for days. You could use X, Y, you could use Q, you could use whatever you want there, a smiley face. Just make sure you tell us what it means. So we start off with $150. And we spend $2 each day. And that is our algebraic expression. To evaluate an algebraic expression, substitute a number for each variable in the expression. Then we're going to simplify using order of operations. So we're going to get rid of the algebraic expression, turn it into a numerical expression, and then simplify. So first thing we're going to do is we're going to take our variables, and everywhere we see an A, I'm going to plug in a -4. And everywhere I see a B, I'm going to plug in a 5. And I'm going to keep the rest of my equation or expression exactly as it is. So 7A we said was -4. And B we said was 5. Big thing to remember here, guys, is anytime we have a number and a variable back to back, side by side together, the 3 is our coefficient and tells us how many times we would have added B together. So it's being multiplied. It doesn't become 35, it's still 3 times 5. Now, order of operations, we use PEMDAS. Says we need to do parentheses first. -4 plus 4 is 0. Bring down the rest of our problem. And again, multiplication here. I suggest that you make your negatives long so you don't get them confused. Like here, that looked kind of like a minus sign. Make sure your negatives are different and you can tell the difference. We check for exponents, there are none. We check multiplication and division. Multiplication. 7 times 0 is 0. 3 times 5 is 15. And we're done with multiplication and division, so we bring down the rest of our problem. Any adding and subtracting, same time left to right. 0 plus 15 is 15, minus 8, 7. Okay, so everywhere I see an X, I'm going to plug in a 1. And everywhere I see a Y, I'm going to plug in a half. So it's going to be 1/2 plus Y is 1/2 squared. According to PEMDAS, we do parentheses, then exponents. So I'm going to take half times a half, which gives me a 1/4. With fractions, we multiply straight across and bring down the rest of my problem. Now we can go ahead and add. Again, with fractions, we need a common denominator, so I'm going to get them both to be 4. Since I multiplied my denominator by 2, I multiply my numerator by 2. I get 2/4 plus 1/4, which is 3/4. Free to pause here and give this a try. X is 6, Y is -3. So 2 times 6 squared minus, in parentheses, we plug in the -3 squared. And it's got to be in parentheses, guys, because exponents come before multiplication and subtraction. So we have to take the -3 times -3 and get 9. And that 9 is what goes in for this exponent here. So when we do our exponents, parentheses first, inside there we have exponents. So 6 squared, 6 times 6 gives me 36. Minus, and again, this whole thing right here is 9. Still in our parentheses. And inside there I get 27. Bring down the rest of our problem. Now remember that our fraction bar is like a parenthesis as well. It's a grouping symbol, so I have to do my numerator first. Then I can divide by 3 and get 18. Example 4 says, in football, a touchdown is worth 6 points, an extra point kick 1 point, and a field goal 3 points. What algebraic expression models the total number of points for a football team scores in a game, assuming each scoring play is one of the 3 given types? Suppose a football team scores 3 touchdowns, 2 extra point kicks, and a field goal. How many points did the team score? So the first thing we're going to do is come up with an expression, and we have 3 different ways to score. We could score touchdowns, we could score extra point kicks, and we could score field goals. And the total score is going to be all of those added up. But the thing to remember is that these aren't all even. Touchdowns are each 6, which means we multiply by 6. Extra point kicks are each 1 point, and field goals are each 3 points. And that gives us our expression. Now, it says the team scored 3 touchdowns, 2 extra point kicks, and 4 field goals. So we substitute those values into our expression. 3, 2, 4. We have to multiply before we can add, and we do that all the way across. Now we add them up and get 32 points. So a lot of you do that in your head. You don't necessarily write out the expression, but you get there the same way, and that's okay. But here I do want you to get practice writing those expressions. So in the got it number 4 here, in basketball, teams can score by making 2-point shots, 3-point shots, and 1-point free throws. What algebraic expression models the total number of points that a basketball team scores in a game? Okay, so we can make 3-point, 2 points, or free throws. And the total is all of those added together. Keep in mind, though, that they're not all equal. 3-point shots are worth 3. Two-point shots are worth 2. And free throws are worth 1. So this is going to be our expression. Now, it says we want to know if a team makes 10 2-point shots, 5 3-point shots, and 7 free throws, what was their total score? Well, we take those values and we substitute them in. 3 times 5 plus 2 times 10 plus 1 times 7. Multiply before we can add. And here I get 42 points. An expression that is a number, a variable, or the product of a number and one or more variables is a term. A coefficient is the numerical factor of a term. A constant term is a term with no variables. And we can add terms to form longer expressions. Like terms have the same variable raised to the same power. We can simplify an algebraic expression that has like terms. We just use the properties of real numbers to combine them. An expression and its simplified form are equivalent, provided you simplified it correctly. Their values are equal for all values of their variable, so that's a good way to check. Plug some values in for the variable, check your answer, check where you started. There's a take note on page 21 that talks about some properties for simplifying algebraic expressions. Definition of subtraction is just adding the opposite, and that's helpful because once we switch it to addition, we can use the properties that we talked about in section 1.2, commutative, associative, things like that. Definition of division is changing from division to multiplying by the reciprocal, and again, that lets us use those other properties. Distributive property for subtraction is the same as addition, except instead of adding, we subtract. Anytime we multiply by 0, we get 0. Multiplication by -1 gives us the opposite. It goes through the opposite of a sum. Make sure you distribute that negative. We subtract everything. Opposite of a difference, same idea there. Opposite of a product, though, keep in mind that product is one thing that's being multiplied, so now it just becomes negative, or the opposite. So if it would have been positive, now it's negative. If it would have been negative, now it's positive. And the opposite of an opposite gets us back to where we started, the original. So the opposite of -a gets us back to a. And I'm going to pause here and we'll finish up in another short video.